Physics 2211 Lab 3 Black Hole. The purpose of this lab is to use computational models from GlowScript to simulate the behaviors and responses of different celestial bodies and objects in space to external stimuli, specifically the gravitational pull of other bodies. This lab is split into two parts. Part 1, analyzing the motion of a star orbiting a black hole of unknown mass to find the mass of the black hole. Part 2, using the calculated mass of the black hole from Part 1, determine the initial velocity a spaceship would need to have to get close enough to the black hole without crashing into either the black hole or the planet orbiting the black hole and still leave the system. We will be making use of Newton's second law and Newton's law of universal gravitation equations. Preview of the results. The mass obtained for the black hole in Part 1 was 1.37145 times 10 to the power 34 kg, and the initial velocity obtained for the spaceship was minus 3.95 times 10 to the power 7 in the x component, 2 times 10 to the power 6 in the y component, and 0 in the z component meters per second. The momentum principle states that the rate of change of momentum is equal to the net force acting on the system, dp/dt, as shown. If we apply the product rule, we can obtain the rate of change of the magnitude of the momentum and the rate of change of the direction of the momentum. d magnitude p dt p hat is the rate of change of the magnitude and the parallel to the direction of motion component of the force. dp hat dt p magnitude is the rate of change of the direction and the perpendicular component of force. So it can be rewritten to show that F net is equal to the net parallel force plus the net perpendicular force as shown. Newton's law of universal gravitation states that bodies with mass attract each other with a force that varies directly as the product of their masses and inversely as the square of the distance between them, where g is equal to 6.67 times 10 to the power minus 11 Newton meter squared over kilogram squared. The magnitude of F net is equal to the magnitude of dp/dt. We can rearrange the formula to find one of the masses. This will come into use later on in the investigation. Note we will be assuming that the only force acting on all the bodies in the system is the gravitational force, as that gives us a general idea of what we are calculating and should be sufficient to calculate the approximate masses. I am using the momentum principle and law of universal gravitation as it helps describe how the motion of the bodies in the system are affected by other bodies. Part 1, massive black hole. Person proceeds to generate unique star trajectory using my emails as shown, gravitational constant is as shown, mass of the star is as shown, delta t for each iteration, which is the number of seconds in an Earth day, is as shown, initial time is as shown, which is 0. Here's how the velocity of the star is calculated. Here's the calculation for each iteration of delta t, and the surroundings is the black hole, system is the star, and initial conditions is t equals to 0. The initial and final velocity of a star are defined here. The initial and final momentum of the star are defined here, calculated from the mass of the star and its velocity. The change in momentum and velocity are calculated here. To calculate the dp/dt for F net, we must calculate the parallel and perpendicular components. To calculate the parallel component, we need to find the change in magnitude of the momentum over change in time, and p hat, which is the direction of motion at that instant. To calculate the dp/dt perpendicular, we must subtract the dp/dt from the dp/dt parallel. Here we use a variation of the equation of gravitational forces in a modified way. Here, one mass is made the subject of the formula in order to find the mass of the black hole. These will be in the vector form because F net is in vector form. Here are the arrows that display the direction of forces acting on the star as it moves. Here I printed out the values of the magnitudes of the forces, and I also printed out the magnitudes of the vectors of the black hole. This would give me a single average value for the black hole. The results of part 1. The black hole mass found is 1.37145 times 10 to the power 34 kg, and the magnitude of F net is as shown. The star follows a specific trajectory as specified from my email, and as expected and also seen from the arrows, the gravitational force acting on the star is smaller in magnitude when the star is further away from the black hole than when it is near it. Now for part 2, initial speed of spaceship to not crash. Here I put the mass of the black hole that I found in part 1, the constants for this calculation, gravitational constants, mass of the planet, mass of the spaceship, delta t, and initial time are as shown, time in which the simulation runs for here being 1 hour in seconds. The initial speed and velocity of the planet are as calculated and as shown. The initial speed required by the spaceship not to crash into the planet or the black hole and travel around and away from the black hole is as shown. These are the values that I was able to obtain from trial and error. The system is the spaceship and the planet, and the surroundings is the black hole, spaceship, and planet because the spaceship and the planet both have gravitational attractions towards each other. The initial conditions is 0. In the while loop here, I calculated R and used that to calculate the net force acting on the planet from the sun and the ship, and the net force acting on the ship from the sun and the planet. I used the velocity update formula to calculate the velocity of the planet and the ship for each iteration. I also used the position update formula to calculate the position of the planet and the ship for each iteration. Here it calculates and prints out whether the spaceship is sucked into the black hole or crashes into the planet. If the spaceship is able to escape, it prints out the distance of the spaceship from the black hole. The results shown, and the initial speed calculated from trial and error is minus 3.95 times 10 to the power 7 in the x component, 2 times 10 to the power 6 in the y component, 0 in the z component meters per second. The initial velocity required for the spaceship to not crash and to get close to the black hole indicates that the spaceship is moving up in the plane and to the left in the plane towards the black hole. When the spaceship gets closer to the black hole, it speeds up, which gives it the velocity required to not crash into the black hole and instead shoot away from it. So what does it mean? How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? As explained in the physics principles section, F net is equals to dp/dt. From this we can deduce that since F net is equal to the rate of change of momentum, then the parallel and perpendicular components of F net are equal to the parallel and perpendicular components of the rate of change of momentum. What initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole? To obtain the initial velocity required for the spaceship to orbit the black hole, I use trial and error. The initial speed required is minus 3 times 10 raised to the power 5 in the x component, 1 times 10 raised to the power 7 in the y component, and per second, and the result is as shown. Sources of error. This is a computational model of the forces that act on a system in space, so may not fully and accurately reflect all the forces acting on the bodies. I use trial and error to determine the values of the velocity in part 2, so they may not be completely accurate values for the velocity required. Thank you.